Okay, we're covering the lecture module level surfaces and tangent planes. And this is right after the module we talked about last time about directional derivatives and relating those to the gradient operator. Okay, so I just want to review something we have so far. What our objective today now is to make a connection between the gradient and level curves and surfaces for a function, and then use that relationship to give us a means for calculating the tangent planes. And that'll come up. It's a useful thing to want to do sometimes when you have this three-dimensional function, is to find certain planes that are tangent or related to that function in some way. And the gradient gives us sort of an automatic way to do that. So just to review for a second, we talked about level surfaces. So if we think about altitude over, like the altitude of Mount Fuji over a region below, and we have some curve looks like this. Let's say this is a level surface for the function. So this would be some surface for which the altitude is some constant. And you could use different constants and get different level curves for a z equals some function of x and y. Okay. Now, if we pick a point here, let's say here, point P, we're going to call that, it's at x naught, y naught. Okay. So that's this location on that level curve. Two things we know now. Number one, the gradient of f at that point will be perpendicular to the tangent to that level curve. Okay, that's the definition of the gradient. It's the direction in which the function changes most rapidly, and that's always perpendicular to level curves, which are curves along which the function does not change at all. Okay. The other thing we know is that if we define this curve with a unit vector r as a function of x and y, the tangent is actually r prime. Okay, if we actually were calculating that. Okay, so that's fine. Now we need to extend this idea to 3D. Okay, so if we think of this in 3D, where our scalar functions are going to have level surfaces, not level curves. So think about like layers of an onion, if you like. If we had a somewhat spherically symmetric function growing out, the level curves for it could be a series of nested concentric circles, or spheres, or paraboloids, or something to that effect. Okay. So the level surfaces for some function f of x, y, and z now, again, no significance to capital F, I'm just choosing that, are equal to some constant, okay? And I could choose a series of different constants and get different level surfaces. Much harder to visualize now, and not easy to sketch, but still the same concept as the level curves we had before. Okay. Now, in this case, like before, the gradient of f evaluated, I'll just say on C is perpendicular to the level surface itself. So if you had a sphere, we'll show this an example. If you had a sphere, which is a level surface, then the gradient would point perpendicular out away from that sphere. One little notational thing that I mention in the notes, when we write something like this here, we write the gradient of f at x naught, y naught. This is not the gradient of f. It's not the gradient of f at that point. It's the gradient of f evaluated at that point. Because f at a point by itself is a constant, so a gradient of that is just zero. It doesn't mean anything. What we're saying here is we're going to calculate, you have f as a function. We're going to calculate the gradient of f to get another function. Then we're going to evaluate this new gradient function at that point. Okay, so it's not just semantic, it's important about the order of this. Okay, so if I had the gradient of this f at some point on this surface, it would be perpendicular to that level surface. Let's just look at a simple example. That, as usual with these things, that helps more than just talking about it. Okay, consider level surfaces for f. X, y, z equal x squared plus y squared plus z squared. Okay, now, this is a sphere, right? That's the definition of a sphere. And so the level surfaces of this are going to be spheres. We want the level surface passing through a certain point, passing through the point 1, 1, 1. Okay? So not every level surface passes through that point. That defines a specific level surface because that gives a constant. So basically we're saying the level surface defined by x squared plus y squared plus z squared equals 3. Because you'd put 1 in for each of these guys, 1, 1, 1, you get 3. So level surface at that. So we're saying x squared plus y squared plus z squared equals 3. Okay? So that's our 3D function. This defines our level surface. Okay? Now if we want the gradient at this point and look at what the gradient will be, we say, okay, well we have f, so the gradient of f, right, will be a vector, which will be 2x I plus 2y j plus the partial derivative of this is vector z, so 2zk. Okay? That is the gradient of this function. Okay? At all points. This function is defined for all of R3, any coordinate x, y, z. This is the gradient at any coordinate x, y, z. Okay? What we want now is the gradient at this point, because this is the point we care about. This point defines this level surface. So the gradient of f at 1, 1, 1 is, well, you put 1s in here and you get 2i plus 2j plus 2k. Okay? So if we try to draw this, and give me back, this vector here is perpendicular to the level surface at 1, 1, 1. Okay? So if we try to draw this, okay, and we say, okay, we're going to look, this will be some sphere, okay, and this sphere has a radius of square root 3, right? Because the general surface for the equation for the sphere would be x squared plus y squared plus z squared equals r squared. So this sphere has a radius of square root 3. The point 1, 1, 1, if this is x, y, z, so we come out in this axis here, so right about there is the point 1, 1, 1. Okay? That's on this level surface. Okay? The gradient at that point is 2, 2, 2. So it's basically parallel to a vector coming from the origin, hitting the surface, and pointing straight out. So it's locally perpendicular to the surface. So if the surface is like a balloon, it's like a pin coming right out of the balloon. Okay, and this vector here, gradient f is like say 2i plus 2j plus 2k. Okay, it's not a unit vector, right? This perpendicular vector, the gradient does not have to be a unit vector. It's just, it is a vector that is perpendicular to the surface at that point. Okay. Okay, so really this is just another restatement of the interpretation of the gradient we had before. Evaluated at any point in space, the gradient tells you the vector direction along which the original function itself is most rapidly varying. And so we have this spherical function which is growing out in spheres. The gradient has to point directly away from the origin because that's the direction along which the function is most rapidly varying. Okay? If I wanted the gradient at some other point in space, -1, -1, -1, then I would get a different vector, right? I'd get -2, -2, -2, and the vector would point in this direction. That's also perpendicular to the surface at that point. Okay, now I want to add a concept here, and that's the concept of a tangent plane. Okay, so almost like from here, if I wanted to consider a tangent, like my piece of paper, that I want to lay right down along, so it just touches the sphere at that point. And then this paper is a plane now that extends in space. And I want the equation for that plane. I want the equation for a plane that just sits tangent to my level surface. And what we're going to say is, okay, well, let's define a plane like that and use the fact that any vector in that plane must be perpendicular to the gradient, and we'll use that to define the plane. And that's what we're going to do. And we'll show you one example of that. So, this is the second part of this note module, tangent planes. Okay. So, if we're going to allow ourselves this concept, let's put it this way. So I have some coordinate system here, okay? And then I have a plane out here, okay, just in general. So if I draw I first identify a point on that plane. So let's call this defined as position vector R0. That is a point on the plane. So R0 is on the plane. And now I want to define the rest of that plane. Okay? So what I do is I say, okay, let's just allow some other general point, R, be on that plane. Okay? And this vector from here to here is R minus R0. Okay? This vector, R minus R0, so it's a specific point on the plane R0, a general point on the plane X, Y, Z defined by R. This vector R minus R0 then is in the plane. Okay? And we're going to use that to define the plane. And basically we're going to say, okay, well, if this vector is in the plane, then I want that vector, no matter where it is, to be perpendicular to the gradient of f at this point R0. Okay? If I think of all the possible vectors perpendicular to the gradient of the function at this point that's on the plane, that'll give me all points that define the plane. Okay? So the idea to say that, well, I want the gradient of f everywhere perpendicular to this general vector R minus R0 is the same as saying that I want the gradient of f dotted onto this general vector to always be 0. Okay? Because if their dot product is 0, that means they're perpendicular everywhere. There's no projection of one onto the other, no non-zero projection. So if I write that out formally, that means the partial of f with respect to x, right, at x0, y0, z0, which is, so I'm cutting the component of the partial, the component of the gradient of f at this point, dotted onto the x component of this, which is x minus x0, plus the partial of f with respect to y, evaluated at x0, y0, z0, dotted into y minus y0, plus partial f, partial z at x, y, z. I'm not multiplying by x, y, z. I'm saying this partial derivative function evaluated at this point, which is on the plane, dotted into the z component of the general vector in that plane. That must be 0. So this gives us an algorithm, though it may not be obvious here. We'll do an example which will help as usual. Gives us the procedure for calculating the equation of the plane. You say, this plane's going to be a tangent to the surface, level surface. I know there's a point that defines that is on that plane. I calculate the gradient of the original function, which is perpendicular to the level surface, the gradient of the function at that point, and I demand that every component of that, demand that vector be everywhere perpendicular to the general R minus R0 vector, which is in the plane. End up with this equation. And this is the equation for a plane. It's not obvious. I mean, it depends, but it's probably not obvious that that's the equation of a plane. But it's a first-order polynomial in x and y and z. Okay? It also captures or includes the point x0, y0, z0. That is on this plane. Okay? Let's do an example. So that's the idea. The note module discusses it a bit more slowly. The textbook discusses it in even more detail in kind of a different way. So you can look at the discussion in the textbook. And this is all in, what is this? This is chapter 9.6 of the textbook, so they discuss this. The note module discusses this more slowly, and then now we're just talking about it a little more quickly. Okay? Here's the example. Here's our function, our scalar function in 3D space, x squared minus 4y squared plus, they don't have to be polynomials, that's what I just happen to be doing right now. Okay. I have this function and I want this level surface. So I'm setting the function equal to this constant. Okay, so this is f of x, y, z. And I want its level surface to be that defined by the function equals 16. Okay? So now I've got this function. This is now a surface in 3D space. F equals x squared minus 4y squared plus z squared is not a surface, it's a 3D function, it's defined everywhere. But as soon as I make it equal to a constant, that makes this a surface, okay, a 3D surface. Okay, no longer just a volume. Okay, so let this, at a point, okay, this is the point I want, 2, 1, 4 on that surface. Okay, and I want to find the equation of the tangent plane to F at that point. 3D function, level surface, so it's going to be a surface. I have a certain point, so this is a big surface. I want a specific point on that surface, and at that specific point, I want the equation for the tangent plane. Okay, so I'm going to lay this tangent plane right up against the surface at this point, and now I want the equation for that plane. Okay. One thing to just kind of quick check is this, we're told that this point is on this surface. Is it? Well, put 2, so 4 minus 4 plus 4 squared, 4 minus 4 is 0, 4 squared 16, 16, yes. So this point is on the surface. If the question said, let f equal this, and this is the level surface, I want it equal to 16, and at a point 1, 1, 1 on that surface, actually, that would be a erroneous problem because the point 1, 1, 1 isn't on that surface. 1, 1, 1 would be 1 minus 4 plus 1, that's not 16, okay? So this point is on that surface, okay? Now I want the plane tangent to this level curve at that point, okay? So we want the gradient. We get the gradient of f, okay? The gradient of f is 2xi, hopefully you can just sort of see this now, minus 8yj plus 2zk. And just while we're doing these gradients, it's not that I'm taking the partial of the first term with respect to x, and then the partial of the second term with respect to y, and the partial of the third term with respect to z. I'm taking the partial of the entire function with respect to x. It just so happens that the examples we did earlier in this module and right now are single term, like this is just x, this is just y, this is just z. So it looks like I'm doing it piece by piece or term by term, but I'm not. The x component of the gradient is the partial derivative of this entire function with respect to x. It just so happens that these two terms give us 0, and all you're left with is 2x. Then I take the partial derivative of the entire function to get this component. The entire function is there's 0 here, minus 8y, 0 here. So it just happens to be that simple, right? Okay. So that's the general gradient. Now the gradient at the point we care about, 2, 1, 4, what is that? So you put x equal to 2, so this becomes 4i minus 8j plus 8k. Okay, so now this is no longer a function, this is just a vector pointing in space. Okay, and it's pointing perpendicular to this level surface. It has to, because that's what the gradient always does. Right? So we know that. We don't have to wonder about it. We know for a fact that this is a level surface of f. This guy here is perpendicular to that at every point x, y, z, and in particular at this point, which is on this level surface, this vector is perpendicular to that level surface as well, okay, at that exact point. So then once I have that, the general equation for the plane tangent to that surface is easy. You just say, okay, well, I'm going to take, remember we say we're going to have the gradient of f at that point, right, that whole thing dotted into this x minus x naught I plus y minus y naught j plus z minus z naught k. Except now x naught equals 2, y naught equaled 1, z naught equal 4. So the general equation then is I take this guy, so I have 4I minus 8j plus 8k. That's the gradient at that point as a vector, dot x minus x naught. So I basically have x minus 2I, and then I take so then I go minus 2 plus y minus, so plus 1. Y minus, oh, sorry, y is not minus 1, y equals 1. So y minus 1, j, plus z minus 4. Okay. So this is the vector in the plane. This is the vector we know is perpendicular to the plane. And now we just do that dot product. The i's go together, and the I dot j will be 0, etc. So we have 4 times x minus 2, okay, minus 8 times y minus 1, plus 8, that's here, times z minus 4, okay, that is 0. Okay, sorry about these ones are supposed to be, this is 0, this is 0. And then you could leave it like that, or you could simplify. I'd probably simplify, so I'd go 4x minus 8 minus 8y plus 8 plus 8z minus 32 is 0. So my equation would be 4x minus 8y plus 8z equals 32. Okay, obviously I could divide this. This really would just be x minus 2y plus 2z equals 8. Just divide everything by 4. Okay, that's the equation for the plane perpendicular to the level surface of this scalar function at a surface value of 16 at this particular point, which is on that level surface. Okay. So it's easy to do in a sense. You just have to sort of trust it a little bit now that we derived it, right? So we have level surface, okay? We have a point. So we calculate gradient to level surface. We evaluate gradient at that level point. When we demand that that be perpendicular to the function x minus x naught, y minus y naught, z minus z naught, where x naught, y naught, z naught are the coordinates of the point on that level surface, which is also the point on that plane, because the plane is tangent to level surface at that point. Okay? And then you require that dot product be 0, and bam, you're done. There's your equation for the plane. You can simplify it, but this is actually it right here. Okay? Okay, so you can go through that. That's just described in more slow detail in the notes. It's also described in the textbook, but it's also something that we have all the tools to do at this point.